Today, I promised that we're going to dive into a very interesting topic and important. For me, it's very important because it was one of the questions that was asked to me during a coding interview. It was about memoization. This is what we're going to talk about. And the coding challenge was about creating a function that has this memoization feature. So as you understand, this can come up as a question or even as a coding challenge in a coding interview, and it's a very important concept in programming in general. So, what is memoization? There is an official definition in the Wikipedia. I'm going to leave it at this point here, and I'm going to start with kind of like a simpler high-level overview. And then we will go into the more technical definition. So basically, we have functions. Let's say, I don't know, do something. I'm out of inspiration today. We have some function that does something and then returns some value. So in general, functions are can be considered as kind of like workers. So you have these workers, you instruct them to do something, usually just one thing at a time. And then when you call them, they execute some code, they produce some kind of like output, and then they vanish. So generally, functions are these one-time things, like these instances that you can call. They do some work, they produce some output, either by returning a value or doing something like drawing something on the screen or sending a request. And then after their execution, they completely vanish from memory. And this is mainly for conservation purposes. A function can run some code, many lines of code. Sometimes it can create variables, it can create, it needs to place things into memory, do some calculation, store some values, access some values, delete some values. And then once it returns the final output, you no longer need to hold these variables that were used inside the function in memory, because if you call a function or many functions and then you get back a result, but these things remain in memory, you end up with a program that will no longer be able like to sustain the current memory of the computer or the browser. So usually functions are things that are called, they start executing the code inside the body, they produce some kind of result, and then everything gets vanished, everything gets cleared from memory. What's left is only the result of the computation, of the execution. The value that you got back, maybe the sum of two numbers, maybe a text transformation or some other kind of like value, or something that was kind of like produced as a side effect. For example, something was drawn on the screen, or maybe a video started playing and so forth. But usually you can think of functions as these things, these workers that you call them, they do something, and then once they complete their work, they just vanish. They move out of memory, and everything gets destroyed and cleared. So if you have a function, you can think of them as this way, like you call a function, and then you get back a result. So call, and then you get back a result. And let me just group this here. And then after you get the result, all this thing here will be like destroyed or cleared from memory, and the only thing that you're left with is the result. Now, if you call the same function again and again, of course, depending on the arguments that you supply to the function, or basically there's something that is inside the function body that get produced, you might get the same result, based on the same input. This is what we call a pure function. You supply the same input, you get the same output. So you'll either get the same result, or you'll get like a different result depending on the arguments. The thing I want to point out here is that every single execution that you see here, so you have like a, let's say, first function call, you get this, you get the result, and then this thing goes away. Then you call the function again, you get some result, and then third execution, and you get some result. So the point here is that every time the function executes, it has absolutely no idea about the past. It knows nothing about whether it was called before, whether some kind of result was produced. So every single function execution is kind of like something that happens in an instant, produces an output, and then it vanishes, and it has absolutely no memory. So it doesn't know anything about the past or about something that happened, before. So memoization, we can think of memoization as kind of like the process of giving the function some kind of memory. So instead of a thing that gets created, executed, then vanishes, and it has absolutely no memory of what happened like before, we give the function some kind of memory. So let me, let's put it here. So with memoization, we introduce the concept of memory within a function. So we say whenever a function gets called, we want that function to have some kind of memory that will be sustained for every call of this function. So if we get, let's say, this function executed the first time, let me destroy. So this is called number one. Okay, this is when we call a function. This is, we call the function after a couple of seconds, and this is, we call it function. So instead of having these isolated function calls that have no memory about what happened before, we introduce the concept of some kind of memory or shared memory between these function calls, so that whenever something happens, this first function call can access or can write to this memory. Let me go here. So it can read or write to this memory. Okay, then of course it will produce the result, and it will also be removed from memory. But the next time that we call the same function again, the second call of that same function can access the memory that might contain a value from a previous call. So for example, if when calling the function the first time, we were storing something like the number one, okay? So let's say that we want to know how many times a function was called. If you have a function and you call it and you call it again and you call it again, it has absolutely no way of knowing whether it was called 2 times before or 0 times or whatever. So if we introduce this kind of memory, we can let the function store some kind of value, some kind of data in this, let's say, function memory. So the next time the same function gets called, it can access through the code that it contains, it can access this memory, it can read the value. So now we can read one that was stored from the previous call. So now this function knows something about the past, that one time that this function was called one time before, and then it can also update the memory. So this is the second time it gets executed. It knows that because it sees the number one, and now it stores back to the memory the value 2. We execute the function, it does something. We once again remove the function and all the variables, all the internal stuff from memory after the execution to conserve space and memory. And then the next time it gets executed, it still can access memory. it can get the value 2, it can update, it can increment this value, so and store it in the memory. So this is kind of like the basic concept behind memoization. Memoization, as you probably understand, sounds similar to memorization. We will see that the reason behind the term is to be able to distinguish behind memorization, which is the ability to memorize, to remember things. Memoization is just more of a geeky term. It's very close to memorization. It was invented, created by some programmers to distinguish from the general, let's say, memorization term, and to connect this term with computer stuff and software. So basically, it's about functions being able to memorize things, to remember things. So this is level one of this very important concepts of memoization. Connecting some function with memory, and then whenever that function gets called again and again and again, it knows something about the past. It can reach out to this memory and do some fancy stuff. In our example, we have a function that can now know and let's say print to the console or print to the screen the number of times it was executed, right? So whenever we call this function, let's say the third time, we can display something on the console like function do something was called third time. Now, this might not sound very interesting, but there are cases when you do want a function to remember something as simple as how many times was it called before. One such example is when you call a function to request some data from a server. That function never gets to connect to the server. Maybe the server is overloaded, maybe the network is down, maybe there's some other kind of problem. So you stop executing the function, you get nothing back, and then you call the function again. You do another kind of like request, trying to get the data. Maybe it's successful, maybe it's unsuccessful. Let's say it's unsuccessful, and then you try a third time, you make the request again, and then you get back your luck and you get back the data. Now, if you remember how many times you have called this function, it's important because if you have some kind of like retrying mechanism where you call the function until you get the data, you don't want this thing to go on and on and on because you'll end up in a kind of like an infinite loop if the server is never responding. So having a function remember how many times it was called in the past can help you in like stopping the execution at a particular point. You say 3 is enough, I'm not going to try again. Or sometimes you want to call a function and make sure that it was called just once. I don't know, maybe you initialize an account, you set a password, you do something that is required to be done only once. You call a function, and then just to ensure that this function doesn't get called again because some bug might be introduced or something wrong can happen, you have this kind of memory, you call the function again, the function sees that it was called once, and then it doesn't go ahead and run some code that doesn't need to be executed if it was already called once. So keeping this kind of like call count in memory can help you in some of these situations. And if you remember in the add event listener method, there is some kind of option, built-in option, where a click handler or an event handler in JavaScript can run only once. This is the second parameter to the add event listener. And that means that when you click, let's say, for example, an event handler gets executed. And if you click again, it will stop executing because the option says run this function only once. So even this simple example can actually help you in a lot of places. So this is kind of like the basic concept behind memoization, getting a function, and then in some way we will see a couple of ways that we can introduce this kind of like memoization, this memory, and you put some memory into the function so that across different executions of the same function, you actually get some shared memory. you store some values, and these function calls can access this memory and do something different every time they're called. So this is kind of like the basic concept. And now I'm going to switch to the, let's say, the more technical official terminology and definition to see this in a more specific context. So the Wikipedia article states that in computing, memoization, or memoization with S, is an optimization technique used primarily to speed up computer programs by storing the results of expensive function calls to pure functions and returning the cast result when the same input occurs. So let's break this down. This once again talks about having putting some memory, connecting the function with some memory, and then when you pass the same inputs to the same function again, you, instead of going through the same calculation, the same process of calculating the results, if the input is the same, you instead return a cast version. So in order to reduce expensive function calls, expensive code from running, if you pass in the same input, you kind of like return something that was cast in the previous execution. So if we go back to this example, let me come up with another example. So let's say now that we have a function that does something like accepts an input. So I don't know, calculate, let's make this heavy, calculation on a number. So you have a function that accepts a number and then returns something that, let's say, it's going to be really expensive. So it returns the number multiplied by a really, really large number. So I don't know, the whatever scientific, I'm using a scientific notation here. So this is a multiplication that is really heavy. It's going to take a while to multiply any number by this huge number. So you call the function and you supply a number, let's say the number 42 the first time, okay? And you call the function accepts the number, the input, the argument 42. It does some heavy calculation. Let's say this is an old machine. This is some code that does more than a multiplication. It takes a few seconds to complete, and it produces the result, which is, 42 multiplied by, whatever, okay, the result. And this roughly takes, I don't know, let's say something that is really a lot in computer interactions. Let's say 2 seconds, okay? Then you call the function again, and this time you pass another number. And you get, of course, the result, which is 24. And let's say that the same time takes to compute this large multiplication. And then a third time, you call the function again, and this time you call the function with the same argument as before, 24, or maybe 42, or maybe some other value that you used like 2 hours ago. This can happen a lot in heavy application with some heavy interaction, where the users interact with application a lot. For example, an Excel spreadsheet. You can guess that a lot of function gets executed, a lot of events happening. Games is something that are applications or software that has some heavy interactions. So you might end up calling a function with the same arguments again and again. Now, in this case, we see how memoization can help us optimize this, let's say, this process. So we have a call to the heavy calc with 42, we get 2 seconds. We have a call with 24, another 2 seconds, and then we have another call to function with 24. So total, we have 6 seconds. Okay, so this takes up roughly, let's say, 6 seconds. So if we once again introduce the concept of memory in this function, I will put a memory here. And we're going to say that we see that we have the same function getting called with 2 times with the same value. And of course, we might want to consider an optimization here. Why do the same calculation when we know that we got the result a few seconds or a few minutes ago? So by introducing memory, we say, let's store the result and the input in some kind of memory. So whenever we call the function, we store both the input and the result of the function with that input in memory. Okay. And then the next time we call the function again, before going into this heavy calculation, we can go into the memory and search for 24. If 24 is in the memory, we can get back the result. In this case, we don't have the result of 24 multiplied by whatever. But so instead, what we do is we store once again the input and the output. So we have to do this heavy calculation, and we store the result of this function call, which I'm going to denote like this. Now, up to this point, we have 2 and 2 seconds. There's nothing that we can save. Okay, so we go into the third function call. In here, we go back to the memory and ask for the number 24. We say, do you have the result of 24? Now, this time, because we stored the result of the calculation 24 a few minutes or a few seconds ago, we get the result in memory. So instead of going again through this heavy calculation, we pick the result and immediately return it from here. So instead of going through this heavy calculation and spending 2 seconds, we might instead spend just 1 millisecond returning the result, which, as you can guess, has some huge improvements if you get a lot of functions a lot of times and with some heavy calculations. So this is basically the essence of the memoization as was described in Wikipedia. Given an input of a function, store the input and the result of that function call to some kind of memory. And then the next time you call this function, instead of immediately going through the same execution again, search and see whether you have the result of that execution with that input in memory, and instead return that result immediately without having to waste any cycles, any CPU cycles and memory to produce the same result. And as you can guess, just storing a couple of values, some inputs and some outputs, usually these are strings or numbers, or sometimes some objects or arrays, they are much more efficient than going through the same heavy calculation many times. And sometimes we're talking about hundreds, thousands, even millions of times and millions of calculations, in a heavy application such as a Excel spreadsheet or a game or even this drawing application that I'm using. So this is memoization, and we're going to see how we can implement this using JavaScript. Before going there, let me know if you have any questions. And I will go through the definition again. So now I think we can understand the definition a little bit more. So it's an optimization technique because we are not wasting memory and CPU cycles to do the same work again. So we speed up the computer programs. It's not only about efficiency, it's also about giving a much better experience to the user. We use it mainly to store the results of expensive function calls. We don't want to do this when the function calls are really cheap. So if it takes a few milliseconds to calculate something, maybe it's not worth to memoize, right? Because memoization, as you will see, has some extra code and some extra logic. It has to do with pure functions. Pure functions mean, let me see if they. So in computer programming, a pure function is a function that has the following properties. The function return values that are identical when they get identical arguments. For example, a function that adds two numbers will always produce the same result given the same two numbers, right? This is pure mathematics. If we add two numbers together, we will never ever get a different result. The same happens with multiplication, division, and so forth. So a pure function means that if you give it the same input, the same argument, you will get exactly the same output every single time. That makes sense because you can memorize something, but you cannot memorize something that given the same input, you get a different output. So if you have a function that, let's say, gives you the current value of a stock, you might say, give me the Apple stock. It will give you, I don't know, $100. If you call the function again after 1 hour, the same input, Apple, IBM, whatever, will definitely give you a slightly different value. The stock value would be $101, 102. So it doesn't make sense to memorize such a function because if you say, given Apple, give me $100, if you call the function after 1 hour, when the actual stock price is gone like to up to $110, getting the cast response, which was like $100 from a few moments ago, it's going to be really, really bad. So if we're not talking about pure functions, we should never use the memoization technique. And the other thing that says is the function has no side effect, meaning that apart from getting an input and producing an output, the function should not go out there in the code or in your app and change things. The only purpose of this pure function is to calculate some kind of new value based on the input. Otherwise, memoization might also introduce problems. There's some other technical kind of like jargon here. I don't want to go into these things. Another interesting sentence is this. It's a type of caching. So caching is storing things. So the next time we want to access the values, we get them faster. So let me see the definition. Okay, it's something that stores data so that future requests for data can be served faster. Um, we have something about the etymology. And in the overview, we also have a nice description. So a memoized function, sorry, a memoized function, oops, what's happening here? Okay, a memoized function remembers the results corresponding to some set of specific inputs. So we can memorize, as we saw in the diagram before, not just the result of one input, but all the inputs. We call the same function with number 2, 3, 4, 5, whatever. We store, every time we call the function, we store the input and the output. So we cast not just one call to the function, but a lot of function calls with a lot of inputs. Subsequent calls will remember with remembered inputs, return the remembered result, the cast result, rather than recalculating it, thus eliminating the primary cost of a call with given parameters. So this is basically the kind of like a technical definition. There's a lot of really interesting things that you might want to read here or should read, I would say, inside the Wikipedia article. Uh, Before diving into the code, let me see if MDN, which is our favorite resource, has something to, has an entry. Yeah, I don't see there's a memoization entry, unfortunately, in MDN. There's a Stack Overflow. So let's start and see how we can implement a simple memoized function. If you have any questions, let me know in the chat while I'm setting up a basic HTML to test this. So, memo. I'm going to add a script and let me call it memo.js. No, sorry, I'm going to I'm going to write some code here. So memoization. And I'm going to, just give me a second to see. So I'm going to open this with live server. So I'm going to right click and open it up in the browser. Opening up the console. Our code is running. Let me also put this here on the left side. And let me add a little bit of styling to make this easier for our eyes. So let me switch to the dark mode. Okay, we have memoization. This is where we're going to experiment with some code. I'm also going to create a memo.js file to create my functions that that are going to be memoized. So let me create a memo.js and close this, and let's put this here, and let's put this code here. Sorry, I have to. No, I think I cannot do this. Okay. So I have to switch between the two. Okay. So in here, I'm going to create a function. I'm going to call it heavy calculation, given some kind of number. I'm going to do something like return num, let's say multiplied by 100 million. I'm going to export this, and then I'm going to use it to and call it in here. So I'm going to say import heavy. It was heavy calc from memo.js. Let's see whether we can console log heavy calc and see something. I will get not a number because I need to pass an argument. So let's put 10. I get the result. Now, in order to calculate the performance and see how long this heavy calculation takes, I can use the performance now API, which is kind of like a very precise way to check the current time. I'm not going to use this. I'm going to use another technique, which is slightly less precise, but it's nice to know, and that's console time. So I'm going to start the timer, heavy calc. So this starts a timer, and then when I want to finish, calculating the time it takes, I'm going to say time end. So we start calculating the time, we calculate, we run the function, and we see that it takes around okay, it's pretty fast, but I'm going to make it slow so that we simulate a slow response. So in order to simulate a slow or heavy calculation, I'm going to go here and I'm going to add some kind of intense for loop. So let counter equals let's say I equals 0, then I is less than, let's make it. So I'm going to just do a very silly for loop, which is going to multiply, I don't know, I by itself, so that it kind of like slows down the calculation. As you can see, just by running a very large loop, we get from 0.0 something milliseconds to 49 milliseconds. I can make this even, I don't know, let's say, and I want you to see something. I'm going to go to 800 million. And I believe that if I, there is a setting that is going to show me a warning when my calculation is slow. So I need to put an event handler. So we will see it in a bit. So as you can see now, we're really running a heavy calculation. And if we run it again, it's going to end up slowing down a lot. We're close to like 1 second, now even more than 1 second. And you can also see the slowness of the interaction of the experience. So if I refresh, you will see we get it result, and then we have to wait 1.5 seconds. So it's going to take a lot. Now, in this case, I'm going to start very simple. I'm going to memoize a function call with input 10. Let's also call it with, let's say, another number, so that we can save a lot of calculations. Right now, we have 4 calls with the same input, 10, and 1 call with 20. So let's go and see how we can improve this and make it memoized. So there are many ways to memoize a function. I'm going to create another version of this. So this is the original slow. And then here is going to be the memo heavy calc. So I'm going to use a different version. I'm going to import it here and replace this code with the memo heavy calc. The same, of course, time. We haven't changed anything. So, okay. So let's introduce some kind of memory. So first of all, let's think what we need. So we need some kind of memory. We need some kind of memory. Second of all, we need a way to store the input, the argument, and the result. Okay. Now, in this case, the input is of type number. We will always supply a number as the argument, and the result will always be a number. So it's kind of like an easy, but we are not confined into memoizing functions that accept inputs or produce, numbers that and produce numbers. We can memoize function that accepts inputs, accept objects, produce arrays, produce any kind of thing. In this case, we're going to start simple. So we need to find a way to have some kind of memory. So you can think about it, and there are quite a lot of things that might come to mind when you're thinking about memory. But basically, the first thing that we should come in mind when we're talking about programming and memory is variables, right? So we can have a variable. We can define a variable. So memory in programming means most of the times a variable. This is where we store things, we store data. Now, this is the simple part. The second part is a little bit more difficult. We have to think about it. So we need a way to store the argument and the result, which basically might sound like we have a pair of values. So a pair of values, argument, and result. So now that we need that we find a memory storage, a variable, we need to find the type of that memory. Will this be a number, a string, a boolean, an array, an object, a set, a weak map, whatever, function? I don't know. But if you get this pair of values, this kind of like key value, you might think that an object is a good candidate for such a memory. So if you want to store these key value pairs, argument, result, input, output, a corresponding value, and a corresponding, let's say, result or something correlated with that value, an object is a good candidate, because an object is all about storing key value pairs. So it makes sense to make this an object. And the rule is that in JavaScript, whenever we define an object, 99 out of 100 times, we need to make it a constant. So we have this memory. We're going to store the results. And how do we do this? So we have to go inside the function. And as described in the diagram, we have to first check whether the input, the number, is cached. Okay, so given as an input, we don't immediately go into the calculation phase. We must first check whether we already have the result, so to skip the long calculation. So we have to check whether the input is somewhere in memory. In memory. If yes, okay, if we do find the num input, then immediately immediately return the cached result. Right? If we find this key, this input in memory, it will be alongside its result. So find the key, find the result, return the result, and skip the heavy calculation. If we don't find it, if no, we don't find this input, it means that we must calculate the result. Then let's say sub step, store the result in memory along with input, and of course return the result. So the basic logic, the basic setup of a memoization is, first we connect the function with a memory. In this case, we decided to go with a variable, and we decided to go with an object. Keep in mind that this might not always be the case. You might do some memoization with some different techniques. Maybe you store something in local storage instead of a variable. Maybe you use an array, or maybe you use a set, or maybe you use another data structure. So depending on the case, you might end up with a different variation of memoization. But the overall idea is the same. Provide a memory to the function, and then go through this basic, let's say, algorithm, these basic steps. So, of course, we get the same result so far. Nothing changed. So first, let's check whether the input is cast. Now, before checking and going to implement this step, we first, of course, have to think how we are going to store into the memory. So this is an object, which means that if you want to store something to the object, you either provide the property name, so key, and then you assign a value. So this is one way of storing a key and a value into the object. Or you can use the bracket notation, so some kind of key with some value. So we know that if we're going to step 2, so if we're going to go here, we are going to use this syntax to store the result in memory, right? The memory is an object, so we have to provide this. And in this case, because the input, the key is the number, here we cannot use this syntax, because this will not save if the num is 42, or in our case, if the input is 10, it will not store a property 10. It will store a property num, N-U-M, okay? So we have to use this bracket notation to turn this value into a key. So I'm going to put this notation. So this is one of the times where using the bracket notations when dealing with object properties in JavaScript is a really good handy syntax to use. And it's probably the only way that we can store such a key in the object that we're using. So this is how we're going to be storing the value in the object. And of course, the way to access and check whether it exists is to use the same notation. So this is a write operation. So object, property, and assignment. And reading is something like this. So if we already have the key num, whatever the value of num is in memory, we check with if memory run. So num is in memory. Let's see whether we find it. We didn't find it. Okay, so we are here. So let's complete the first step. So if we find the value inside the memory, then what's our idea? Immediately return. So in here, I'm going to memory num. This is the easy part, right? Find in our memory bucket this value, the result of num, and then return it. And we will skip all the rest of the code. By returning early here, the rest of the code, the slow code, will never get executed. Usually, oh no, okay, return. So still nothing here. Let's check our assumptions here by manually adding the property. So I'm going to do something like this and see whether, oops, that works. So it works. Of course, the result shouldn't be cast, but you see that instead of getting 1.8 seconds, we now are down to 383. So we have this really fast cast response here and here. And I think what slows the whole process down is this. Okay, we don't have the number 20 cast, so this ends up slowing down the process. If I now add 20, we will get, as you can see, 0.2 milliseconds, which is really, really fast. So our assumptions are, I think, correct up to this point. If we find a way to store the cast values, we can speed up the process. You can see this is a huge improvement from 1.8 seconds to 0.2 milliseconds. If this was a game, this was a great boost. So we have this. We might check about our implementation in a bit, but for now it seems that it's working. So let's go here to the next step. So if there isn't the key inside the memory, which is the case for 10 and 20, what do? We store the value in memory. But first, we have to calculate the value. Okay, so if this is the result, so we go through some, let's say, simulated heavy, kind of like process. We get the result as we described in our steps here. We must replace each comment, each step with the actual implementation, with the actual code. So store with the result, right? So this is the step. Then let's implement the last step, which is to return either the result or memory bracket num. So now we can return this or this. They actually point to the same value. So return result to skip on another unnecessary operation, which is to access the property of an object. So if you think that returning this and this is the same, it's not exactly the same, because this is going to return a variable. This is going to find this object and try to find and access this property. So we have actually two operations. In here, just pick this variable and return it. Accessing an object property might take a little bit more. So just to skip a few more CPU cycles, I'm going to return result. And let's see right now what happened. So let me just, so we start with line 19. So in here, we have the first execution. And then, as you can see, we don't see the message here. Let me change the message. Is in memory. Let's make this, I don't know, something like this. Okay. So in here, we calculate, nothing happens. Why? Because the result of 10 is not in the cast memory. Then we run this again, and we get the result. Still slow. This is on line 20. But next time we call the memoized function with 10, you can see that we find 10 to be in memory, we return it really, really fast, and we skip a few seconds or a few milliseconds. The same thing happens here and here. So we get two costly, let's say, calls to the function. This must be executed. We need this, otherwise we wouldn't get the value. But we optimize this by a lot. We saved like 3 calls to the heavy calculation. So we went down from, let me comment this code. So we went down from almost 2 seconds to like a huge improvement, almost it's double, or we have the operation, the calculation time. So this is a very simple implementation of the of a memoized function with one input. Okay, so I have to notice that we are memoize a function based on a single, okay, this is important, on a single input or argument. Okay. And the challenge for you would be to think, memoize a function with 2 arguments. And then maybe an even harder challenge, memoize a function with more than, with or 2 or more arguments. Because it's often the case where you don't just get a single argument, you get a function with 2 or more arguments. For example, you might want to draw something on the screen. You probably need an X and a Y, 2 arguments, 2 coordinates, or find something on the map, or add 2 numbers. So if we had the function called add that returns the sum of the 2 numbers, you can simulate some slow code here for loop. So what you will need to do is to grab this function and transform it into a memo add, so that when you get the same arguments, like 3 and 4, every time you get 3 and 4, you get the same result. So you can cast it, and if you call the function add with 3 and 4 10 times, you will immediately get the cast result. The first time you need to do the calculation, of course, but you will need to and then you cast the response. Something that is a little bit challenging about this kind of functions. So, for example, when you're working with arithmetic operations like addition, multiplication, these are commutative operations, which means that it doesn't matter if you add 4 and 5 or 5 and 4. If you switch the operands, you get the same result. So we have commutativity here. So A and B equals B and A, as A times B, B times A. So you have kind of like a sub-challenge here, which is going to be tricky. Or BA, meaning if you say add 42 2, you must also memoize this and return the same result if you get this kind of like input. So run the function 42, 2 with 2 arguments the first time, calculate, store the cast result, run the function again with 2, 42, you will have to get the cast version because the result will be the same. So this is a little bit tricky, and it of course has to do with these arithmetic operations which have this property of commutativity of having the same result, no matter the order of the operands. So this is the kind of the more advanced. Now, let me go one step further, and instead of doing this here, let me add another. Let me put it here. And I'm going to run something. I'm going to create two buttons. And I'm going to, you can try almost this is, and for now, I'm just going to comment this code so that we get a slightly cleaner output. Now, I'm going to go one step ahead, and instead of just running this function, randomly or directly through the program, I'm going to create two event listeners, two click handlers, so that this heavy calculation function is executed whenever we click one or the other button. And I'm going to use document, query selector. I'm going to grab the first button. I'm going to use the first child selector to click. So console log 1. So an event listener for the first button. It cannot read. Okay, so I'm running the script with type module, which means that it has to wait for the DOM to load. At this point, it has to wait for the element, the button, to be rendered in the page. So I will use another event, the DOM content loaded, to ensure that the DOM content has been loaded, and then run all the code that can access the DOM, because at this point the DOM is not ready. The code is running way too fast for the browser. Let's see if we get so DOM content loaded, and then we get button first. Okay, it's I think I have a mistake with the selector. I'm using first child of a parent, but as you can see, the button is not the first child of the parent. This is the first child. So I have to switch to nth child and get the second child. So this is the first child button. The first button is the second nth child. So I'm going to use this. So this works. Let me create another handler for the second, which is the third child, starting from the parent. This is the third one. So let me see. 1, 2. Okay. So I'm going to run a function, and I want to have a different result, a different execution whenever I click 1 or 2. So let me create a function that will do something a little bit different. So I'm going to create another function, and I will put this here. So I'm going to say export function count me, which is going to return, or let's say console log, the number of times this function was called. So this function was called something times. So I don't know, we'll see, times. Now this is a variation. We have a function that every time that we call it, I will skip the slow simulation for now. So every time I call it, either through this click handler or this click handler, Count is not defined. Yes, because I have to import it. Okay. So now whenever I call this function, I get the same, exactly the result. I can memorize or memoize this function, and this function can remember some previous value. It can remember how many times it was called. So I'm going to memorize or memorize a function. This time I will not be using any arguments, even though we can. So I'm going to define a memory or let's say counter count memory. I'm going to start with something simpler. I'm going to say, let's make this 0. And now, instead of just getting the same result whenever I call the same function again, I'm going to be displaying this variable, count memory, which is going to be 0, either from the first handler or the second. And then I want to, whenever this function gets executed, I want to increment the count memory so that I keep a memory. I keep the function remembering how many times it was called. So I can use the either this operator, which is going to be a little bit difficult to read here. This is very confusing, but it will do the work. Assignment to constant variable. Of course, I have to switch to let. So the function was called 1 time, 2 times, 3 times, 4 times, from the other 5, 6, 7, 8. So we have a different variation of a memoized function. This time, no arguments, a different memory, a simple number. We don't need key value pair, and different result, different effect here. We don't return a value. We just console log something. Or we can, of course, return this concatenated string and console log it on the call function, on the call site. So return this as a value and then console log it, let's say, right here. Now, this is another example of a memoized function. So let me change this to, let's change this to count memo, because let's export this and make sure that it works. Okay, it works. That's another example. I'm not slowing this down because I don't want right now to kind of demonstrate this concept. I think we already demonstrated this. Also, in this case, we do not have an input, so we will always like just see this console log. And this, as you might guess, is not a pure function, because given the same input input is always empty. So this also is kind of like thinking as the same input. The same input, if it's empty, it's kind of like the same, but we get a different output. So this is not a pure function, because every time we call it, we will get a different effect, a different side effect. The console log that is going to be different 1 times, 3 times, and so forth. So this is a little bit different from the previous implementation, which was purely a pure function. Now, the reason I'm going to this simpler example 9 right now, even though we're deviating from the pure functions, is because I want to demonstrate another thing. And that's that we have this function, which, let's say, it's really helpful because it keeps in its memory the previous number of executions, and you get to see this, 13 or whatever, and then you can also use that value to stop the execution if you reach a certain number, a certain threshold. So if you reach 10 times, don't execute it or do something different. But the thing here is that we're restricted to counting the executions of a single instance or a single let's say, version of this function. What do I mean by that? Is that if I click 2 times on the first button, I see, let me refresh. So I see 1 and 2. Now, what if I want its event click handler to use a different memoized, let's say, instance, so that we start counting from 0 when I click on number 2. So I want number 1 to use like its own memory, and then I want the click handler 2 to use its own click handler. So there's going to be like one version of let's say, count memo here. So I click it 1, 2, 3 times. And then I have a different version here. So a different count memo that is going to start counting from the beginning. And it's going to stop, let's say, on the first one. And this is going to be running its own memory. So we have the same function with memory, but we want these two to have their own memory. So this kind of like a little bit more advanced. So we want to create like something like copies of count memo that will have their own memory. So we can execute these copies or these different instances, see something, see a memoized, let's say, a property, see like a value being displayed or kept in some kind of memory, but we want to have one or more, two or more like versions, so we can count in a different context. So in this case, just two different event handlers counting something. Maybe this is a game, and you want to count how many times the player clicked on number one, on button 1, how many times they clicked on number 2, or did something with button 1, or did something with button 1. Now, so how do we address this? One simple way would be, of course, to create two different functions with two different memories, right? So we get count memory 2, count memo 2. Okay, pretty easy. We import it, and then we store this, we execute this here. And now we have two different memoized functions. They're both memoized. They both keep some memory, and they remember how many times they were called. So we have 1, 2, 3 times. This is count memo, a memoized function. And then here I have another similar function with its own memory. So we can now use a memoized function, not just for a single instance, for a single like case, but we can also use it in another context because we want to use like a different memory. This can work in a simple example, but there are some disadvantages to this say solution. So first of all, we want exactly the same function to do exactly the same thing, but have a different memory, which means that if for some reason I want to change this function slightly, so this function was, let's say, executed, I have to change all the copies, all the occurrences of this function. So if I want exactly the same behavior, I have to go here and I have to go here. So changing the function means I have to change it twice or thrice, or maybe I have 5 buttons, maybe I have 10 buttons. So one thing that's not very practical is to find all the places where this is defined or copied and change this. The other, of course, obvious is that you're going to end up with a lot of code. So what if this function contained 200 lines, right? You had 400 lines containing the same code. And of course, the worst thing is that if you need this function 100 times, what are you going to do? You have to copy the function 100 times. So this is not how we work in programming. We have to automate things and find smart ways. So instead of using this solution, I'm going to use something that's a pretty powerful feature of JavaScript, which is high order functions. Higher order functions are functions that accept or return functions. So basically, when some other languages allow you only to pass um, functions that accept um, uh, functions as arguments or return arguments, but some programming languages just allow you to pass simple values to a function and return simple values, meaning simple values, an array, a boolean, a string, a number. With JavaScript, you can use functions. You can actually think of functions as values. So you can pass them to functions as arguments, or you can return them as values. So we're going to use this very powerful feature of JavaScript to create a function that is going to be returning a function. So this is going to be kind of like a creator or a factory function that is going to return as many memoized functions as we need. So I'm going to create a kind of a copy of the count memo. Let's call it inner. And I'm going to return it. So this is how a higher order function looks like. It's a function that it returns a function. I can define the function here and then return it like this. Or I can immediately put the return statement before the definition. It's the same thing. It's up to you. So I'm returning a function that is going to do exactly the same thing, like console log, something like this. This, let's say, inner function, let's slightly change it. So exactly the same function, but we're returning it from another function. And in here, I'm just going to say, I'm going to define the memory here. I'm going to call it a different name so that we don't confuse these two. So here's what we have done here. We created a function whose sole purpose is to generate, to create, it acts as a factory to generate and return some function. So this function will be called, and it will return a new function. So the result or the return value of this function will be another function, which is going to be ready to be called. So if I say const m create count memo, what this function will return is this thing here. So m is this thing here. So let's check it. So a higher order function just returned a function, not just a simple Boolean or a string or a number, but a function. So this returns back this, which gets stored in this variable. So this variable now holds a function. And as functions are a bit more powerful than simple values like primitives or arrays and objects, we can also execute them, right? A function is executable. So if m contains this function definition, this function reference, I can call it and see some kind of code. So let me call it 3 times, and we get exactly the same effect. So we created a higher order function. We defined a variable that will act as the memory to this function. So this now is connected to this function. And the way that these two are connected together is by a thing called the closure. We call the function, we get back the returned value here. So you can think of it as this function getting executed, and then this is the return value. This will replace this function call, right? And this return value will be assigned to this variable. So you can think of this function call as working this way. Get this return, the thing that was returned, and pass it on as a value to this. So every time I call this, I will get back a new function. Now, the cool thing is that now we are not restricted to just a simple instance of this memoized count memo inner, which is going to be, you know, displaying the 1, 2, 3, 4, 5. But we can call the create count memo as many times as we want. And let's see what's happening now. And now we have a different version, a different instance of a memoized count memo inter. So in here, we call the factory, we call this function that generated this and returned this function with its own memory. We call it here. So executed once, executed twice. Next, we call the create count memo function again. So this function reruns again from scratch. It redefines a new variable inside its scope called count memory inner. It connects this with this function through closure. This is inside the scope of this function body. The function can access the scope of this function, so they are now connected together. This gets returned as a new copy, new version, a new instance of this count memo inter. And in here, I have a new instance of this function with a new instance of its memory. So it's a completely different count memo inner with a completely different count memory inner. And now when I call it 3 times, I see 1, 2, 3. So it starts from scratch because it was initialized with count memory inner 0. When I continue the execution of this first memoized function, I continue where I left off. 1, 2, 3, 4. Okay, so we have two separate memoized functions with their own memory. So just to give you a diagram of what we did is if I have this, we call it count memo inner, or I don't know, let's call it M. Okay, so we have this M, and it has its own, let's say, memory. So memory. And then every time we call it, or let's call it, let's use the name here just to be a little bit more precise. So we call it once, twice, and again. And since we can keep things in memory on every execution, like how many times, let's say, it was called, we get, you know, a different result. But we created another copy that lives its own life. So we have another copy. This is M, and this is M2. Two memoized functions, they share the same memory whenever they get called, but there are two instances, the two versions, the two different memoized versions. And in here we get, of course, completely different universe. We have, you know, different calls, different numbers, and so forth. So they now separately live their own life. They have their own memory, but they're two distinct memoized version of our count memo inter. And of course, we can use a loop, or we can create as many instances of this memoized function as we want. And we can reuse it every time we want in a different context or in a different part of our application. In this case, I use like a very simple function that does only one thing, like console logs the number time of execution. Remember that this thing, this is an impure function. Why? Because given the same input, it produces a different output. Count memory will be 1, 2, 3, 4. So even though the input is the same, undefined or empty, we get the different output. So it's an impure function. And also it has side effects. It console logs something, so it doesn't return a value. So it does something somewhere on the browser. So this is kind of like considered a side effect. But the most important thing is that the output, like the thing that you see when you execute this function every time is different. So it's impure. But I wanted to use this so that we can kind of like see it a simpler memoized example. So even though the description, the definition said that we should be using memoization with pure functions, you can see that sometimes this can also be effective and maybe practical and useful, even though the functions are impure. Um, and we use the power of the the higher order functions to actually create more than one version of a memoized function. And of course, if we were to pass arguments to this function, so if we wanted to, let's say, make this pure function and maybe pass some values, so 3, 4, we can definitely do this. We can pass an argument here, and we can switch back to the pure version of our function. So we can actually transform this into a higher order function that returns a pure function. So that is another challenge. So I'm going to state here, so challenge, create a higher order function that returns a memoized function that adds two numbers, and let's say another one. Oh, let's keep it here. So take the knowledge from this heavy calculation, but it was a pure function. Transform it into a function that accepts 2 arguments instead of 1. Memoize it, see that it works, and then create a higher order function that will give you the ability to use not just to create not just an instance of one memoized add, but more than one. So if this was kind of like if you create this function create memo add. So let me put this at the end because I think that's the hardest challenge. So if you implement this, you would be able to see something like memo add 1, and then memo add 2. So you will get 2 versions of the memoized add function, and then you can say memo add 110, 20, and then so this would return. Okay, but you can also have another version that keeps its own memory. So memo add 1 will keep the input 10 and its result. It will keep the input 20 and its result. But memo add 2 will contain a completely different memory. It will start with an empty memory, and then you will get something like 44, 33, 10. So the same functionality, the same behavior, but with a different memory. So you will get something like this. Memo add here, memo add 2, and you will be able to use it in 2 or more different locations. So imagine that this is a game and you have like some kind of like heavy calculation going on a function that, let's say, calculates the energy from a character every time they hit something, or every time something hit them. So you create a memoized function to reduce, let's say, the number of operations, because if you hit some target with the same, let's say, power, you get the same result. So you can optimize there. But you have many characters in your game, so you don't want one memoized function to calculate, to have the same values and calculate the same results for all the characters. You want each character to use its own memoized function, so that they produce a much faster result and better experience. But each character must have their own memoized kind of like special function. So a game might be a good candidate for using many versions of the same memoized function. As I mentioned earlier, a spreadsheet or some other kind of board game or other applications. So let's recap. Let me take a look to see whether I have. Yeah, I have one last thing to show, and then we will wrap up. So I mentioned earlier that if a function call becomes too slow, we will get some kind of like a warning in here in the browser. So the browser is smart enough to remind us that something is really slowing the application down, and it might have some implications in the user experience. So if I click a button and it takes, let's say, 1.8 seconds to do something like before, that means that the application is going to be really slow. So if I use that slow heavy calc, let's say that let's use it in here, which was like, this is the, remember, the non-memoized version, which is taking is way too slow. Memad, yeah, I have to comment this here. Okay, so this should work after the implementation. Now, I have this heavy calculation. Remember, this is not memoized, this is not optimized. So when I click it, you will see that it took 377 milliseconds. So when the handler or the function call, it's becoming too slow, or it's taking, I think, more than 200 or something milliseconds, you will get this kind of violation warning. So it says that something is really slow in your application. It shouldn't take almost half a second to do something. So go there and check what's happening. And in our case, it's the heavy calc, which is running this slow code. If I make this even slower, you will see now it's almost half a second. Let me get down to 700, because maybe in a different computer. And now you will see it becomes unresponsive. So I click it and it continues executing after I clicked. The click is not fast enough. So that's why we get this this violation warning, because it becomes slow and unresponsive to the user interaction. So we have to do something in here. So when you see this message, you will probably seeing this because some function is taking more than it should. If I try just to see, uh, you can see even in 191, I think it's 100 milliseconds, the kind of like the threshold. Yeah, so 3 million, 300 millions. Yeah. Anyway, I think it's around 100 milliseconds that you get this this warning. And if we were to time this, I think we would see the same result. So yeah, you can see we can time it, and the violation also calculated the before and after in some way when we clicked, and then when the execution was finished, then it says, it took quite a lot of time. Let's see. And now I can click, and yeah, once again, we're kind of like it's rounding down the time of execution. So that's the last thing I wanted to show. It's not something that has to do with memoization. This can happen for all sorts of reasons. You will get this warning if your code is slow. And this is a place, of course, where memoization might prove to be, an optimization might prove to help you make this click handler work faster. Sometimes you just need to refactor your code because even if I memorize this function, it will take 400 milliseconds the first time. So maybe even that is not a good user experience. Also, sometimes you cannot just memorize a function, right? Maybe this is an impure function, or maybe it's doing something that it's really hard to memorize. So you might want to refactor, or at least take notice of this violation, this warning, and go into your code and look and see how you can improve it. So let's recap, and then you'll be able to work on these challenges. So we saw memoization, which is a general computer programming concept. It's basically a way to optimize functions. We memorize functions. Usually, it's pure functions that we memorize. So, given the same inputs, we get the same output. So, it makes sense to cache the result and return back the cached result if we get the same function call with the same input. Once again, do this only if it's a really slow, costly operation. If it takes a few milliseconds, you don't need to memorize your function because the whole process of creating memory, checking in memory, and doing all these things might prove to be more costly than just letting a function run in a few milliseconds. So don't just memorize all the functions. Make sure to check the Wikipedia article, and make sure to work on these challenges. So thanks for watching, and make sure to practice on the concepts.